Okay, so we're going to take a look at our warm-ups. Today we're back to ACT warm-ups. So you have 3 to do here, and this should be in the 4th column on your warm-up sheet. Just be sure to label it today's date and 7, 8, and 9. And when you're ready to check these, go ahead and press pause now and give them a try. And then when you're ready to check, press play. Okay, let's talk about these. This first one says it's a geometric sequence, and if you remember, geometric is where we have a multiplier. We call that a common ratio. So this is the formula we learned for geometric. It's the first term times the ratio to the n minus 1. So our first term is 1, the common ratio is -3, and we're looking for the 7th term, so we'll raise it to the 6th power. Now, even if you didn't know this formula, and I know we're going to talk about this formula again here shortly, but even if you didn't know this formula, you could have just kept multiplying by -3 until you got to the 7th term. Now, the second one's a word problem, but it wasn't too difficult. It was a fee of $10 plus 65 cents a pound, and there's the work. The next one, we had this chip. It has a top and bottom, and the thickness of the top and bottom together is 6/100ths of a centimeter. So if we subtract that out, that leaves us with 26/100ths of a centimeter. And if each layer is 2/100ths thick, we divide those two and we find that there are 13 layers. Okay, so we're going to take a look now at the problems from your worksheet we didn't get to, that we didn't do together the other day. So here are the ones you were supposed to complete, 1 through 12. And if you will just correct these, and when you are ready to move on, you may press play. So go ahead and press pause so you can correct, and press play when you're ready to move on. Okay, now I wanted to talk about just a couple of these individually and then give you the answers for the rest. Okay, remember the 1/2 power is the square root because the bottom number is our root. The top number of a rational exponent is our power. So if it's a 1/2, it's just square root, and the square root of 25 is 5. So if we had a 1/3, it's just cubed root. But if we look at number 6, it's not just 1/3. It's -1/3. So we do the reciprocal. And we're taking a cubed root of a negative, which is possible, because -6 times -6 times -6 is -216. Now, generally, we don't leave a negative in the denominator, so we would move it to the numerator. On this last one I'm going to talk you through, the denominator is 5, the numerator is 3, so it's the 5th root of 32 cubed. Well, the 5th root of 32, what number times itself 5 times is 32? That is 2. And 2 cubed is 8. All right, go ahead and check the rest of these, make corrections where necessary, and if there's something you want to ask me about later, put a big star beside it, or some type of notation that lets you know you'd like to ask me about it later. When you're ready, pause this now, and when you're ready, press play. All right, so this was simplest radical form and rewriting with a rational exponent. So, number 11 we had done together, so let's talk through number 12 now. This is the 5th root of z to the 11th, which could be written as power over root, z to the 11/5. Now this is a nice form to help us simplify. Remember to put this in simplest radical form, you say, okay, how many times does 5 go into 11? Well, that's twice. So 2z's, z squared comes out of the radical. How many were left over? Well, 5 goes into 11 twice, and there's 1 left over. So that 1 that's left over must stay in the radical. I'm going to rework 16 so you can see it happen. So all of this is a cubed root. So what this means is like 8 to the 1/3 power, x to the 5/3 power, and y to the 6/3 power. Well, 1/3 power is the same as cubed root, and this simplifies completely. The cubed root of 8 is 2. And then 3 goes into 5 one time. But we have 2 2 left over. 3 goes into 5 once with 2 left over. So that leftover must remain under the radical. And then 3 goes into 6 evenly twice. So all of that together is our final answer. Okay, I'm about to show you the answers to some of the remaining problems. Please make sure you make corrections. And then any that you still need help with, please put a note beside so you can ask me about those later. Okay, go ahead and press pause. And when you're ready to move on to correct 17, press play. All right, here's 17 through 20. So on 17, when we think about this as a to the 4, 6, b to the 8, 6, c to the 12, 6, do you see that all of these can reduce? Take a look. Whoops. These reduce. So when they reduce, the 4, 6 reduces to 2/3. The 8, 6 reduces to 4/3. That helps us to get it in the simplest radical form. Now, 3 does not divide into 2. 2 is smaller than 3. So A remains completely under the radical. Nothing can come out. But 3 goes into 4 once. So 1B comes out and 1 stays under. Now 6 divided into 12 evenly 2 times. So that's where the C squared came from. All right, we'll take a minute and check the rest of these. Anything you have a question about, make sure you ask me when I return. Okay, today's notes. Now you should have picked these up when you walked in, but if you didn't, go get them off the bookcase now. And we're going to take a look at exponential growth and decay. The first thing we have up here for your benefit for you to use is just some powers. These are numbers squared to the third power, to the fourth power, to the fifth power. And you can refer to this table when you're working some of these problems. Now, you studied exponential equations in Algebra 1. So some of this is going to be a review to you. You're going to go, oh yeah, I remember that. And then some of you are going to have some nice big cobwebs. And you're not going to remember this too well. So we're going to go through each part again. So any function that can be written in this form, where we have a constant times a base raised to an exponent, that's considered to be the form where we can model exponential growth or decay, depending on the value of the base. So, if our base is greater than 1, we consider that growth. And if our base is less than 1, but it has to be greater than 0. So between 0 and 1, it is considered exponential decay. Now, when we have a real live quantity, and this is kind of important, it increases by a fixed percent, the amount of the quantity after t years can be modeled by this equation. A represents that initial amount, and R is our percent. Now, when we look at R, so here is our equation. Y equals, not Y, excuse me, this is generally with population. Population is equal to the initial amount times 1 plus or minus the rate raised to the number of time periods. So when we do this rate that is a percent, we need to always change that to a decimal. Now remember, if we had 5% and we rewrote that as a decimal, we'd move the decimal twice, so it'd be 0.05. So when you plug the rate into these equations, make sure you do change that percentage to a decimal. So that quantity, 1 plus R, is called our growth rate. Now, if it was 1 minus R, instead of growing, it would be getting smaller. That's our decay rate. Okay, So let's look at some examples that are similar to some you already did back in Algebra 1, but we probably don't remember. So let's pretend like we've never seen them. So in 1972, that was a great year. That was the year I was born. Figures provided by the UN showed that the population of the Republic of Korea was 32,530,000 with a growth rate of 2.2% per year. So for that rate, we're going to change that 2.2% to a decimal. Move it twice. So that is 0.022. At this rate, what would be the expected population in 1994? So to answer this question, we need to model this situation. The population with respect to time is that initial population, that 32,530,000, times the growth rate in this case, 1 plus the rate because it's growing. All right, and this is T for time in years, and this time is the number of years after 1972, because that's what the problem was referencing. So in part A, if we're looking at 1994, how many years after 1972 is 1994? Well, in that case, the population in 1994 would be modeled by this equation. For the time, because it is 22 years after the initial year, what we would plug in for T is 22. And so we would get an approximate population of 505,375 people. That's what our population would be in 1994. Now, because this is already passed, we normally don't use population models to determine populations in the past. We normally use them to predict populations in the future. That's where they're most helpful. Part B, though, reads, the 1995 World Almanac lists the 1994 as 45,083,000. What is the difference? Okay, so this is what we estimated the population would be. This is the actual amount. So all we would do is subtract these two to get the difference. So we were quite a bit off. We were 7,422,375 people off. All right, let's take a look at the next example. Example 2 says, a physician gives a patient 500 milligrams of an antibiotic that is eliminated from the bloodstream at a rate of 8% per hour. Predict the number of milligrams after 4 hours. So I'm going to work number 2 over here. So we need to know a couple things to plug into our formula. Oops. So in this case, our initial amount was 500 milligrams. This time it is being eliminated. Eliminated is decay. That's where we're going to do 1 minus the rate written as a decimal. Now, T is time, and in this case, it says per hour for 4 hours. How many units of time would that be for this particular problem? That would be 4. Now, if it said it eliminates 8% per half hour, then this would be 8, because that's how many time periods there would be. If it said it eliminates 8% every other hour, every 2 hours, then this would just be 2. So you have to determine what your unit for time is for your given word problem to decide what goes here. Okay, so when we plug this in, we're going to get that we have 358.2 milligrams of medication left after 4 hours. Now, did you notice with the people, I didn't have a decimal? You have to be careful with that. You have to work within the context of your problem. So with people, we're talking about wholes. But with the amount, a measurable thing, this is discrete, this is continuous. So I can have a decimal here. Number 3 reminds us of our compound interest formula. And we also studied this in Algebra 1. So this is our compound interest formula where P represents that original amount, R is the interest rate written as a decimal, N is the number of times it's compounded per year. So if we saw words like annually, annually happens once a year. Semi-annually happens twice a year. So that would be a 2. Monthly occurs 12 times in a year. Weekly occurs 52 times in a year. Daily would be 365 times a year. Oh, one that I left out, quarterly. You hear this a lot with business. Quarterly would be 4 times a year. So this problem says share and invest $2,500 at an interest rate of 9%. How much is it worth after 10 years if compounded annually? That means once a year. So when we come in here to use our formula, the amount remaining after 10 years, or the amount total after 10 years, not remaining, because this is increasing, it would be 1 plus the rate, 9% written as a decimal. How many times is it compounded? Annually just means once a year. But if this were any of these words, it would change to that. So if it were quarterly, that would be a 4. If it were monthly, that would be a 12. All right, raised to the n times t. So number of times is once, t is time in years, and in this case, we're doing 10 years. So we're going to plug this into our calculator. And let's see what we get. So we do 2,500 times 1.09 to the 10th. And this would give us a total after 10 years of $5,918.41. Now, an interest rate of 9% is currently unheard of. I think I make maybe 1/4% on my savings account right now, 0.25%. It would be lovely if I could find this type of interest rate, but it currently doesn't exist. All right, so after taking these notes, you should be able to do most of the problems on the back. I expect you to at least to give a good effort on all of them. You must have attempted all of them to get full credit. So the back is your remaining classwork / homework. And hope to see you tomorrow.